what is latency? Latency basically is the delay in transmitting data. Basically is from the input of the transmitter to the output of the receiver, electrical. So it's the electrical in and electrical out. And there are many causes of to generate this latency. Of course, now the latency we are concentrating on is the transceiver, right? So on the host side, on the ASIC side, there are requirements for latency. I'm not talking about that. I'm just focusing on transceiver latency. So the second question is that do you know if latency is important? And I would say it is. I remember deal with several customers requesting shortest latency from the transceiver, which we deliver to them. Why? Some of them are the enterprise fiber optic networks. They specialize in financial institute. So you can imagine fiber length, right? The path being equal, if, from one city to the next, beyond the same, and the switch beyond the same. The only difference is the transceiver latency can be different, and it just happens that this parameter can be optimized. So for instance, to meet the 10G transceiver requirements, which is usually like 3 nanoseconds some years ago. So let me go on to the next one. And here's, I want to give you some perspective in terms of number. For the free space for the light traveling is like a 3 to the power of 8, right, meter per second, which translates to 3.34 microsecond per kilometer. Now for a single mode fiber with the refractive index 1.4682, it translates to about 5 nanoseconds per meter. See? So you might not realize fiber can be delayed that much. Now, again, for what 10GI is, like 100 picoseconds eye opening, right? We call it 1 eye. So 5 nanoseconds is equal to 50 eyes. Now for the 25G, nowadays, is 40 picoseconds per eye equals to 125 eyes. So what I'm telling you is that the delay, you have to search frame by frame and so forth. Make sure you can locate the right pulse as your reference. Sometimes can be a headache, but sometimes you can do it with some control. And the one down there is typical requirements. Again, I already say that it's 3 nanoseconds for CR, 10G CR. So this slide shows how the customer would like us to measure. Basically, it's from the input of the transmitter to the output from the receiver, right? So there are 3 ways to do it, basically. One is to create a specific bit pattern. Because when you use a pseudo-random, you don't know which one is which. So sometimes you might need to create a specific pattern for it. Sometimes you don't have to. And then the other thing is that in order to measure, people use high-speed probe to measure. That can be problematic because the probe carry capacitance, which can distort the rise time and fall times to directly affect your measurement. And I use the third one. I use the pattern that I know, and I use mainly calibration to help me to measure this. Calibration, I will show you, can be done properly, that you can measure without error. Now, this block diagram, I put it together as how you should measure. Let me explain. This side is a pattern generator. It goes on to a reference transmitter, EVB, I call it. Here I have a reference transmitter, and the light, the transmitter light going into the DUT. Now, there's a DUT device under test is the module we're going to measure. And then the output from the transmitter going through the traces on the EVB, a looping cable, and traces on the EVB into the transmitter side and transmit to O to E units of the DCA, and it triggers by this pattern generator. So basically, the first time there are two blocks. The first block is this block, generator, EVB, reference transmitter, DUT, delay, loopback, I call it loopback cables, including the traces on the board, and into the O to E. That's I call it A. And the second one is, again, go back to here, pattern transmitter, EVB, reference transmitter. Now you unplug this and unplug this connector and mate it with the LC connector. And this path, I call it B. This one has to be calibrated out. You can see when you calibrate out, you don't care what it is. So I will show you how to do that. So that's what I call it B, by mating with the LC to connect this point with this point. Okay. So basically, this repeats what I said. I'm not going to say it. It's just mainly I mentioned on the previous page, just here for documentation purpose. Now here I took some pictures. It was done before. And you can see this is like a generator with a reference transmitter, right? And with some cables. I don't care what the cable is because this whole block is going to be calibrated out. And then the transmitter would drive the receiver here, right? This is a DUT now, DUT. And then those blue cables, I call it loopback cable, right? And then going back, this cable going back to the transmitter, and transmitter going through this fiber, I call it A, and then B somewhere here. So, and I also show you on the DUT EVB, there are traces here. We had to calibrate it out. Let me go back just a little bit here. Here, these traces we need to, in fact, from here all the way to here, we have to subtract out. This is not part of the DUT. Okay. So let me go back. So I took a picture and showing you the traces. Okay, so here's the calculation. Yeah, here's the calculation. Here's the calculation. Now, as I mentioned, path A is everything all the way. So going back here is everything all the way, including the DUT here. You measure one time. Second time, you measure the one without the DUT. And here, again, I go back to show you. The second one, you measure here. You made these two cables with this adapter and measure again, okay? So very obvious, A minus B, the difference is 6.707, right? But also you remember this difference also include the onboard EVT traces, right? The RF traces and also the loopback cable. So for the RF traces, the EVB is Rogers 4003C with the dielectric constants, roughly about 3. It's 10G. Basically, to be exact, at about 7 gigahertz. So some of you can just using your standard calculation to calculate the delay, which ends up for the length of 4.72 is about 0.752 nanosecond delay. This can be measured or can be calculated, pretty close. And the other one is the cable delay, right? So we just measured, it's a 5.171 nanoseconds. And you put everything here, you subtract out this 6.707 by those two variables, and it ends up like a 0.784 nanoseconds. Here is your latency of the transmitter, from here to here. So very easy. I just want to show you this simple technique because some people struggle with difficulty. They do not have this block to subtract out, so they have to trace each point of that, and it becomes a lot of headache. Try to find where the pulse is. So I just show you a simple way to do it. I hope in your later on you understand how this is measured. Even you can measure with the EVB. Now I would think inside the switch is very hard to measure, but you can bring it out, just set up like my block diagram using the EVB. You can do it with no time. Okay, that's my sharing for today. How to measure latency. There are any questions?
Eric, I see a question. Can we measure the I parameters using any software or any scripting language?
I parameter, you mean, what do you mean by I parameter? I would think what it means is, yeah, you know, measure, basically let me ask you, let me reply to you right now. So basically what you're talking about to measure the rise time of basically you measure the rise time of the signal, not the jitter, right? The jitter, there are many lines. Rise time, if you do correctly, you can do in the middle of the jitter, you can have your own rise time, and you measure that with the reference point, which is basically you can say 50% of the eye height at that point. Yeah, so there should be no program. This is a very manual measurement. You don't need any program to measure. Everything is manual, right? Analog, by hand, manual, right? The one I mentioned is the specific pattern you might want to generate. For instance, you might want to program a bit like a 1 and then 0, 0, bunch of 0, and then 1, 1, 1, you know, to identify your leading bit, so you can locate the bits to count it with reference to delay. So sometimes you can use pseudo-random because the pseudo-random, they do kind of repeat in a way, so you get confused which bit to count. But sometimes you can count it if you do carefully. There's another question, is the process same for PAM4? That's a good question. Yes, so if you are familiar with PAM4, what the PAM4I is measured every time by an equation to averaging all three I's together, all of the rise time, all the fall time, all the different levels together, right? So to find for instance, the rise time, right? So, but you need to average out all three eyes together. And there are ways to do it on PAM4. They take care of that. So yes, but I would think PAM4 is a little bit harder to measure because the jitters are much more. Yeah. So, but I think by following the technique to measure the PAM4I, you should be able to find your rise time edge. Yes, at the 50 points, 50% points. Let me see. There's no more questions. You can ask me about the question by emailing to sending email to Priya.
Yeah. So thanks, Eric, for a very interesting session, and thank you all for joining. Like Eric said, if you have any questions, please send me an email, marketing@vitextech.com. We'll be posting the recording of this webinar tomorrow on our website. So I shared the link to it in the chat. Next week's topic is OSNR and sensitivity on Thursday, again at 4 p.m. We hope to see you back then. Thank you, everyone. Bye.